Good morning, students. So, in the last class, we discussed about the derivation of packing efficiency of FCC. Okay. So, in the today's class, we want to discuss the same derivation, but for the packing efficiency in BCC. You know that BCC means body centered cubic cell. Okay. So, initially, the main one is writing the structure. This is one cubic cell. Otherwise, I take here. It takes a lot of space. Okay, so students, this is body center. So I'll just draw the structure in such a way. Center of the body we have empty space. Like this. This is A, B, C, D, E, F, G, H. So in that body centered cubic cell means the constituent particles are at the corner position along with it at the center of the unit cell. This is body center. So students, we are considering this point and this point. Remembering front one this is, middle and the back one. Are you getting? So this one is the, okay, here is the center of the body. Okay, this one. Okay. This like along the diagonal we are considering from weight. Okay, listen, this one point. Here the body center I am drawing here. Okay, these are the corner positions. We are considering from here to here. Means from this end to this end. This end to this end. The body diagonal. Okay, next. Listen here. So then we considering these 3 points. Take this one as the center. Draw the diagram. Spheres. I will just draw the diagram here. Another sphere. These two are the. This one is the body center. The way to write the body center cubic cell. This point, this point, this point. Okay? And students remember, here we need to find out this one and F. Are you getting? So we need to consider A and this point and this point. This one means like this. We need to consider the triangle means from here to here, here to here. It is not the joint, you know. Are you getting? Here to here, here to here. We need to join this. Then this is the triangle. We need to consider this triangle. So students, this one is no, you know, this is face above, below. So this is E, F, D, C is a face, one of the face of the cube. Here listen, take the edge length like A. This is face diagonal B. This one is body diagonal C. Then the radius R, 2R, R. This is the diagram. And the diagrams are very, very important. Why? Why? Because if there is no diagram, we cannot derive the derivation. Okay, listen. Initially, we need to write the given dot. Let edge length be A. Next, let edge length be A. Next, face diagonal length. Face diagonal length B. Next, body diagonal length. B, C. Edge length A, face diagonal B, body diagonal C, and radius of sphere B. This is the assumption. Okay. So students, first we need to identify our of this FD. Okay. Select triangle. This one. FCD. EDF. Anything. Okay. Just like triangle FCD. EFD. Okay. So listen here. This is the hypotenuse. These two are the sides. So from the triangle, it is a right angle triangle. From this is the hypotenuse. That is FD square is equal to EF square plus ED square. I am not telling you need to take only this one. You can take this one also. Okay, I'm not telling you need to take only this one. Okay, you need to take this one. That's your choice. But the correct derivation for your convenience, this is the correct one. So FD square is equal to EF square plus ED square. FD square in here is what? B square. This one is A square plus A square. So B square is equal to how much? Totally 2A square. Remember this equation. From this triangle EFD, FD square is equal to EF square plus ED square. B square is equal to A square plus A square, that is 2A square. Just read. Next, we know this. Now we need to consider the triangle AFD. Okay, consider from triangle AFD. So students know that this one is R you take instead of AFD you take ADF because this is 90 degree. So students, this is the hypotenuse, same right angle triangle. That is AF square is equal to AD square plus FD square. AF means what here? C. C square is equal to AD. It is a line, so A square. FD means B. B square. So C square is equal to A square plus B square value what we have here? 2 square. Substitute here. So 2 is 2. C is equal to square root of 3A square. Okay. C is equal to root 3. This is equation 1. Second one. From figure. Okay, from figure, C is equal to R plus 2R plus R means 4R. That is equation 2. Next, from 1 and 2, left hand side both are same, compare this, root 3A is equal to 4R. Because C and C are equal, from 1 and 2, these two are equal. So A is equal to 4R divided by root 3. This is what edge length. So once we got the edge length, we need to calculate volume of the cube. So volume of cube is equal to A cube. So A means how much? 4R divided by root 3. That is 4 4s are 16, 16 4s are 64. R cube divided by 3 root 3. This is what? A cube. Volume of the cube. Next. Once we got the volume of the cube, next volume of the sphere is equal to 4 by 3. One sphere you take. One sphere is equal to 4 by 3 pi cube. Next, total volume of sphere in PCC is equal to 2 into 4 by 3 pi r cube. What is this 2? That is the number of atoms per unit cell. So total that is 6, 8 by 3 pi r. So we got volume of the cube and volume of the sphere. Apply the packing efficiency formula. Packing efficiency is equal to total volume of the sphere divided by volume of the cube into 100%. Okay, then here total volume of the cube, here it is 64 r cube divided by 3 root 3 whole divided by volume of the sphere we need to write, that is 8 by 3 pi r cube whole divided by volume of the cube, that is 64 r cube divided by 3 root into 100. R cube get cancelled, 3 3, 8 ones are 8 8s. Then totally you will get 68%. This is the derivation of body centered cubic cell. Are you getting? Initially, writing the diagram is important. Considering the sphere is also important. Without diagram, you won't get any marks. Because where can you show A is, B is, C is, R is if there is no diagram? How can you take from triangle, from this triangle to this triangle if there is no diagram? How can we see? So listen. Without diagram, you are writing. Consider the triangle EDR. Consider the triangle EFDR. Consider the triangle ADF. From where we need to consider the triangle? From the diagram. So diagram is very, very important. So this is the most oftenly asked question, both FCC as well as BCC. Okay, for 3 marks. Remember, very easy and 100% questions. So the thing is what? Initially we need to find A cube, then sphere, then the percentage. Okay. So this is packing efficiency in basics. Next, packing efficiency SCC in simple cubic cell. So the diagram for that is simple unit set. This is A, B, C, D, E, F, G, H. Simple cubic cell means the constant particles only present at corner positions. There is no any other positions. There is no face, there is no body. Okay, now consider this one as the point, center point, like the sphere. Bigger one. This is one sphere. So consider this one as the point, write the another sphere. This is the diagram. Adjacent sphere we are considering. Okay, like this. Listen, 1, 2, 3, 4. These two we are considering. Understood? So from here, students, this one is R, this one is R. Of course, all are A. Here only let H1 be A and radius of sphere be R. Only two assumptions are there. H is A, radius of the sphere is R. Directly take from the figure, this anyone A is equal to R plus R, that is 2R. We know that directly numerate A, that is H then, that is equal to R plus R, 2R. So then, volume of cube is equal to A cube, that is 2R whole cube, that is 8R cube. Okay, next one is volume of one sphere is equal to 4 by 3 pi r cube. So total volume of sphere in SCC. In SCC, number of atoms per unit cell is 1 and that volume is 4 by 3 pi r cube. Okay, then it is of course 4 by 3 pi r cube. So then apply the packing efficiency formula. Packing efficiency is equal to total volume of sphere divided by volume of cube into 100%. Total volume of sphere is how much? 4 by 3 pi r cube. Volume of the cube is 8r cube into 100%. If you just cancel this, that you will get 52.4%. Means the lot of empty space is there. 52.4%. Okay, so this is all about the derivations of packing efficiency of SCC, BCC and FCC. So students remember, another one also you maintain end center. So end center means any two ends. Everything follows FCC structure, but at the volume of the sphere is 2 into 4 by 3 pi r cube, then the percentage decreases. Okay, so this is all about what? Packing efficiency. A very important derivations. Okay, so the next one is, in the last class I told you that is voids, means the 74% it is completing when we arrange in the FCC manner. Okay, so I'll write here, in FCC structure, packing efficiency is 74%. In BCC, packing efficiency is 68%. In SCC, packing efficiency is 52%. We know that. So what is the remaining part? That is empty space. 74% means in the 100%, 26% is empty space. Here 32% is the empty space. Here 48% is the empty space. What are those empty space? Why they are formed? Okay, that is called as voids. Gaps, that is called as voids. gaps which is formed while arranging the constituent particles in the form of a manner. What is it? In a regular pattern. Okay, in the form of a sphere. So in that case, one dimensional is there. In one dimensional, there is no gap. Just simply I'll explain the structure. There is one dimensional structure. Here there is no gap. Okay. So here one sphere is touches to two spheres. So coordination number here is 4. Sorry, 2. Here I write. In one dimensional structure, only one type is there. Dimension type. And the next one is coordination number. So one dimension, one type, coordination number is 2. Okay? Okay, so the next one is two-dimensional structure. What are those two-dimensional structure? By using one-dimensional structure, we need to frame a different structure by arranging in a row or in a column. So listen, this is one structure. I am continuously arranging them in this manner. So I just write, I consider only 4 spheres here. 1, 2, 3, 4. It is one-dimensional structure. This one-dimensional structure can arrange in 2 ways. So that is from 1, it is 2-dimensional. So listen, one way is like this. Means the first sphere, the first layer, this is the first layer, and the second layer. The first and the second layer are exactly one above the sphere. Listen, they are exactly one above the sphere. Even the third layer is also same like that. This is the fourth layer. Means the one-dimensional layer is continuously arranging in such a way the spheres of both the layers are exactly one above the other. Exactly touches each other. Then, if you consider one circle here, so listen, how many circles it is going to touch? From here 1, from here 2, from here 3, from here 4. So if you join the centers of the neighboring circles, then which structure we are getting? Square. So this structure is called as square close packing. Okay, here the coordination number is, what is coordination number means? The one sphere touches how many spheres? Initially in one dimension, listen. So this one sphere touches 2 spheres. Here one sphere touches 4 spheres. So coordination number is 4. So another way of arrangement is there. So this is one layer or one dimension layer. Okay. So the second layer is like this. Okay, listen, this arrangement is like A, and A. Here it is A, this is B, this is A, B. A type arrangement, A B type arrangement. So means here if you consider this sphere, here also it is touching, here also, here, and here. Means if you join the centers, the 6 spheres are touching. So coordination number is 6. And the shape of this is what? Hexagonal. This is hexagonal close packing. This is square close packing. Means in one dimension, this type of structures are there. Hexagonal close packing, but square close packing means one dimensional structure are arranged in line. So if it is exactly above the first layer, then square close packing structure will form. If it is at the depressions of the sphere, means if 2 spheres are there like this, this portion. That is what? Depression. So another layer spheres are fits here. Means if the spheres are fit at the depression of the initial spheres, are the layers of the first layer. Second layer spheres are fits at the depressions of the first layer spheres. Then it is hexagonal close packing. Here in the two dimension types is there. One is two types. One is square close packing. Another one is hexagonal close packing. I just write this. See, square close packing coordination number is 4. Hexagonal coordination number is 6. Next comes 3 dimension. Next comes 3 dimension. Means by using 1 dimension, we did 2 dimension structure. By using 2 dimension, we have to construct the 3 dimension arrangement. Okay. Next, assume this. Okay. So students, this is the square close packing structure. By using square close packing structure, we are doing what is that? Another 3 dimensional structure. We are continuously arranging them. Listen. So another layer I'll arrange in the backward. So another one. Okay. So another one. 4 layers I am arranging. Listen. If you join the structures here, 1, anything you are getting? It is like a structure like this. This is exactly the structure of a cube, perfect cube. Means if square close packing structures are arranging in such a way, the first layer arrangement is also A, this is also A. If A type arrangement is there. Okay, so then what happens? These form cubic close packing. This shows cubic close packing. And remember, here one sphere is there. So in the in a one layer, it is at the one sphere is bonded to 4 coordination spheres. Means the one sphere in the same layer bonded to 4 other spheres. So we are keeping above one and below one. So this is the one layer, okay? This pen is the one layer. It is exactly touching 4 spheres in the same layer. So I am keeping another one layer here, another one layer here. So when the above and below layer are kept for this layer, then this sphere touches one sphere in the above layer, one sphere in the below layer. Just assumption. So then it is 4 in the same layer, 1 in the above layer, 1 in the below layer. So coordination number here is 6. This is one thing. By using square close packing, here cubic structure will be there. Here the coordination number is 6. By what? By square close packing structures. So another one is there, hexagonal close packing. I just wrote this because I need to explain what is voids. Okay, so listen, I'll consider first layer of hexagonal close packing. I'll consider only 4 spheres here. This is one layer, hexagonal closed pattern. Here void is nothing. Okay. Next as well, the second layer is placed here. Of the depressions, this is the depression point. It's placed here. Next, another one. Next, next. Okay, listen, this is closing here. These are closed. Next, another one. They are the depressions, right? One, two, three. So listen students, here also this is closing. Okay, means when the first layer, and just to show you like this, 1, 2, 3, 4, 5. This is one layer. The second layer is at the depression, is like this. Means these are closing here. The structure is like three spheres of one layer and one sphere of another layer. I will completely shade this. Okay, three spheres of one layer and this is one sphere of another layer. When the three spheres of layer are joined, then they create a void here, gap. Are you observing? I will write the big one here. I hope you can see the void here, gap. Okay, this gap. This gap is closed by one sphere of the other layer. So that is called tetrahedral void. Why? Because we are using 1, 2, 3, 4 spheres. They are arranged in a tetrahedral manner. Means listen, one sphere, two sphere, and this one is the third sphere. Okay. 1, 2, 3 sphere. And they have another one sphere. They are like tetrahedral manner. Getting means I hope how to show you. Listen, one sphere, two sphere, three sphere. They are arranging in this manner. 1, 2, 3. Okay. So another one, I'll just take this. Okay. This one is like this. This is closing the gap. This is what? Is it these are in a different plane? This is like this, closing them. So they form a tetrahedral structure. That's why they are called as tetrahedral voids. Means one layer of this is, so one hexagonal layer is placed over another hexagonal layer. They form different types of void. One is tetrahedral void. The structure of tetrahedral void is the spheres of one layer is closed by the sphere of another layer. It is completely closed. This is tetrahedral void. So another one type is like listen. This one, this one, this one, and this one, this one, this one. Here, this is layers of first layer. When the other layer is placed, the spheres are like this. Means here the void is created like this. So students, this void is empty. Okay, this type of void is octahedral void. Why it is called as octahedral? It is formed by 6 spheres of in a different. So octahedral means 6. The structure is 1, 2, 3 sphere. So this is 1, 2, 3. This is what? Octahedral void. That is always empty. Okay. So the next one is, so listen here, if number of atoms is equal to n, a capital N unit, then number of octahedral void also equals to n, and number of tetrahedral voids equals to n. This is the formula. If number of atoms is equal to n, and the number of tetrahedral voids is equal to 2n. Later I will write what is this n and 2n. Octahedral void and tetrahedral void means. Okay. So this is arranging the second layer over first layer. Another one layer is there. Means placing third layer over first layer. Listen, this is A type arrangement. This one is B type arrangement. Okay. Next, in the arrangement of third layer, 2 ways are there. So AB type arrangement, closing tetrahedral voids means here the voids are created. Those voids, those gaps are covered. Means if the structure A is there and the structure B is there, then the third structure is equal to A. Means the third structure is exactly placed at this A. Means the third structure is same as arrangement of A. Here, the same one. The star structure is also same as arrangement of A. AB type arrangement. So then that type of closing octahedral voids causes hexagonal close packing structure called as HCP. Hexagonal close packing. And remember here, so students, in the one sphere, consider in the one sphere, in the hexagonal close packing, we have coordination number 6. So when the above that sphere, if another sphere is placed, listen, 1 to 3 spheres further touch with what? 1 to 3 spheres. Or one sphere, consider one sphere is again touches the 3 spheres. So in the below layer 3 spheres, above layer 3 spheres, same layer 6 spheres. Total here coordination number is 6. So here in the hexagonal close packing, that is HCP, coordination number is 12. 6 in the same layer, 3 in the above layer, 3 in the below. Next, another one is there, that is closing octahedral voids. Closing octahedral. Listen, tetrahedral voids are here, octahedral voids are here. I'll just mark this. Octahedral voids are here. Then this is the first layer A type. This is the second layer B type. If the octahedral voids are here, the third layer should be placed here like this. Are you getting? Then this is C type arrangement. If the arrangement is ABC type, then it is cubic close packing. Then it is cubic close packing called as CCP. It is also having coordination number 12. So another one is cubic close packing, that is CCP, coordination number is 12. So this is all about the arrangement of atoms in one dimension, two dimension and three dimensional structure. Understood? So listen, in one dimension coordination number is 2, they are arranged in a straight line. In two dimension, two types is there, one is square close packing, another one is hexagonal. In square close packing, 4 coordination number is 4. In hexagonal close packing, coordination number is 6. Third one is three-dimensional arrangement. By using square close packing structure, if we keep on arranging the structures, then we will get cubic structure. It is not cubic close packing. It is perfect cubic structure. The coordination number is 6. Next, another one is by using close packing structure, three ways are there. One, placing the second layer over first layer. Here the first layer is there. This is the second layer. Placing the second layer over first layer. Upon that, what happens when we place the second layer over first layer? They form voids. One is this type of tetrahedral voids, another one is octahedral voids. Tetrahedral voids and octahedral voids. This is the formula to calculate. So students, third layer. Once the second layer is placed over first layer, we get voids, tetrahedral voids and as well as octahedral voids. Okay. Once, okay, voids are created, then the placing third layer is of two types. One is closing tetrahedral voids. We need to place the third layer in a such a way it should cover all the tetrahedral voids, then only the octahedral voids remains. Then the type of arrangement is AB, AB, AB. When the tetrahedral close packing will take place, tetrahedral voids will close when the first layer, third layer arrangement is same. A, B, A. Third layer is equal to the first layer, then that is tetrahedral void close packing, that is called as hexagonal close packing structure. Next, another one is closing octahedral voids. Octahedral voids are here. So first layer is here, second layer is here, third layer is here. If the type of the third layer is not equal to the first layer structure, that is ABC type arrangement, then they form cubic close packing CCP. In both the case, the coordination number is 12. So students, here this FCC, HCP, CCP all are having same type of arrangement. And remember another one is right in the SCC. This is also equal to SCC. This is FCC. Okay, this is simply this is three-dimensional structure. So in BCC, the coordination number is 8. Remember that. For BCC, the coordination number is 8. Okay, so this is all about the close packing structures. This is all about the voids. The tomorrow's class I will explain. So how many, if a number of atoms are equal, then how many voids are formed, how many tetrahedral and how many octahedral. So otherwise I write now only. Listen. So listen. This is unit cell or number of atoms per unit cell, means N1. This is tetrahedral 1 is equal to how much? 2n. I will take octahedral. Okay, next one is tetrahedral void. How much equal to 2n. So in number of atoms in unit cell, that is type of cell. Assume SCC, number of atoms is 1, octahedral is 1, tetrahedral void is 2. Next, in BCC, number of atoms is 2, octahedral voids is 2, tetrahedral voids are 4. Next, in FCC, number of atoms are 4, octahedral voids 4, tetrahedral voids 8. In ECC, number of atoms 2, octahedral wires with tetrahedral wires. This is how to find out the octahedral and tetrahedral wires in different unit cells. This is if the number of atoms is equal to n, number of octahedral wires is also equal to n, tetrahedral is equal to twice of n. Okay, so this is all about the arrangement. In tomorrow's class, we will discuss about the different defects in the arrangement of the atoms. That is, means vacancy defect, Finkel defect, Schottky defect. Those defects we will discuss in the tomorrow's class. Thank you.